Hello everybody, in this video I would like to tell you about Jordan's lemma. It is named after the French mathematician Camille Jordan, and it's a very nice and very useful lemma in complex analysis. So let's go over its formulation. So let f be a function from the complex plane to itself, and we assume that f is just an integrable function as opposed to the typical situation in complex analysis where f is some analytical, holomorphic, or some nice smooth function. Here we just assume that f is just an integrable function, and when we say integrable we mean integrability in the sense of Riemann. That means that the real and the imaginary parts of f are Riemann integrable functions, and we can also talk about integrability in the sense of Lebesgue, but it will be outside of the scope of this video, but it can also be generalized to this even more general class of integrable functions. An integral function in general, it even doesn't have to be continuous. So let us assume that this function is bounded on this circular arc CR. And then if we look at this set, just ignore the supremum for a moment, the absolute values of f of z when z is in CR, then this is a set of real numbers that is bounded by assumption, right? And therefore, by the axiom of completeness, there exists a least upper bound or a supremum. So we will denote by mr the supremum of this set, right, which exists. And then we can state the following inequality: then for every omega in R holds this inequality. So it is bounded. So in itself it's kind of nice. So if f is bounded, so one corollary would be that when omega tends to infinity, it's just like this Riemann-Lebesgue lemma in a sense, right? Then if omega tends to infinity, then this integral tends to 0. But and I just illustrate the CR. This is CR. This is this semicircular arc, right? But what we really want and what is really useful is the following corollary. So if in addition to what we have said before, we assume that f is also bounded on this arc CR, but on every type of this arc, starting from some R0, right? So for every R that is bigger than R0, we have that f is bounded on this arc CR, and this least upper bound on CR, right? Because here on CR, we know that f of z is bounded by this least upper bound mr, and if this least upper bound tends to 0 as r tends to infinity, then we can deduce that this limit exists, and actually this limit is 0. Now, why is it useful and why is it so important? So it's supposed to remind you the Fourier transform in a sense, right? Because what we want to compute in a Fourier transform is this integral from minus infinity to infinity of some function, right? Say f of x e to the I omega x. This would be the Fourier transform. And the definition of this integral would be, in a sense, this limit as r goes to infinity. Yeah, we have to assume that it is integrable, but one interpretation of this integral would be that this integral, this limit when r goes from minus infinity to infinity of fi x e to the I omega x dx. Now, this integral can be difficult to compute, and suppose that we want to invoke the residue theorem, right? So I will just describe the typical situation that happens when the Jordan's lemma is applied. So what can we do here? So this is the complex plane. This is minus r, and this is r. And what we would like to do is we would like to compute this integral. And we would like to use this residue theorem. So we would construct this circular arc CR, right? And then the residue theorem would say that the integral of minus r from minus r to r of f of z e to the I omega z dz plus this integral over CR of f of z e to the I omega z dz equals to 2 pi I, the residue of f at some of the residues, right? At some points z, k from 1 to m, right? And those are the poles, or the singularity of this function f. Now, in the typical situation, this is something that is relatively easy to compute, right? We can compute it. And if we would hope that as we take r to be larger and larger, this would tend to 0, then we would just have this integral, this limit that r goes to infinity, from minus r to r of f of z e to the I omega z dz, that this integral is actually equal to the sum of residues. It's 2 pi I sum of the residues of f at those singularities that k goes from 1 to m. Right? So, and the Jordan's lemma really helps us to find or formulate a simple condition on f when we can hope that this integral will tend to 0, and then this Fourier transform, this is just this integral f of x e to the I omega x dx from minus infinity to infinity can be evaluated as this sum of residues, right? So this is why the Jordan's lemma is so nice and useful, and it's typically applied in those situations. So now let us prove the Jordan's lemma and see. It's kind of straightforward. So we want to evaluate this integral over CR of f of z e to the I omega z dz, right? So we need to choose a parameterization of CR, and well, we will just take z to be r e to the I theta, where theta is in 0 pi, right? And so we would look at f at r e to the I theta. The integral will go from 0 to pi, and then we have this complicated expression. Not so complicated, but we plug in what we have. It's r e to the I theta. So it's in a sense e to the I theta, right? And this expression here. And then finally dz is I r e to the I theta. So we plug it in and we get I r e to the I theta d theta. That's the integral that we need to compute. So now if we take the absolute value of this, right, then by the triangle inequality for integrals, we have that this is less than the integral of the absolute value of what's inside. And the absolute value of what's inside is r e to the I theta absolute value. And here, the absolute value of e to the I theta is just 1. So here we get another r. And here, that's the expression that we'll need to work with a little bit. E to the I omega r e to the I theta d theta. Okay, and one more thing, this is by assumption is smaller or equal than mr, right? So we can say that this is not more than mr, it's bounded by mr times r times this integral from 0 to pi of e to the I omega r e to the I theta absolute value d theta. Okay, now let's use the Euler formula for this and actually recall that e to the I theta is cosine theta plus I sine of theta. And if we plug it in, then we have e to the I omega r cosine theta plus I sine of theta, which is e to the I omega r cosine theta, and cosine theta times e to the minus, right, I times I is minus 1 omega r sine of theta. Now if we were to compute this absolute value of this, it's the absolute value of this, which is equal to the product of the absolute values. Now again, this is a real number, and this is e to the I, this real number, and we know that the magnitude of this is 1, so we're left with this expression, right? So if we get back to this integral, then we get this chain of inequalities. So this integral that we're talking about is bounded by mr times r, and now we need to compute the integral from 0 to pi. This is actually a real number, and it's a positive number, so e to the minus omega r sine of theta d theta. So up to this point it has been rather simple and rather straightforward, and now comes the ingenious part of Jordan's lemma. So this integral is very hard to compute or to estimate, right, because of this nonlinear term. And in fact, if you would like to use it's some kind of Bessel function here, but if we would like to use this method of the fundamental theorem of calculus when we find the primitive of this function, then actually there is a theorem that says that e to the power of this sine cannot be expressed in elementary functions. So we would like to, since we're interested in upper bound, we'd like to bound it from above by a nice function that we can actually compute. So when we have this complicated exponent, our best hope is to use some linear function to obtain a bound on this sine of theta, right? And so if we look at the graph of the sine of theta, if we plot it, say, from 0 to pi, that's the graph, right? But by symmetry, sine here is symmetric over this pi half, right? And so by the way, if we look at this expression again, so if it wasn't for this sine, right, it's quite easy to integrate it. It's quite easy to see that, okay, when r is big, e to the minus omega r is going to be small, but then there's this sign, and at 0 it is 0, and at pi it's also 0. So how do we actually find an accurate bound? So if we look at this sine function, and we look at this interval over here, then we can see that this is a convex function, and therefore this line lies below the graph, or I mean concave. It's a concave function, and therefore every at least in this interval from 0 to pi half, every linear segment connecting any 2 points on the graph will lie below the graph of the function, and we can actually find the equation of this line. So, and yeah, that sine is concave can actually be proved quite easily. Just compute the second derivative and this interval, and you'll see that it is negative. So therefore it's concave, right? Because the derivative of sine is cosine, and the derivative of cosine is minus sine. So the second derivative, so sine of theta, second derivative is minus sine of theta, and when theta is at 0 pi half, then this is concave function, meaning that every line that joins every 2 points on the graph will lie below the graph, and therefore the equation of this line can be easily found. So when it's pi half, it attains the value 1, right? So it goes through 0, so its slope is actually 2 over pi theta, and there we have it. We have this inequality, which is quite simple. Sine of theta is greater than this, right? At least for theta, which is in 0 pi half. And moreover, we see that here it is symmetric. The sine is symmetric above this pi half. So we can actually say that this integral is bounded above. It's mr times r, and then twice the integral from 0 to pi half, and here it's going to be minus omega r, and instead of sine theta, we will write this. It's 2 over pi theta. So it's a pretty good bound, and this is the best linear bound below on the sine function, right? Because we want to bound it from below, so that because of this negative sign, then it's actually the result is something that bounds this from above. And well, you can try and to maybe improve this estimation, right? But it's not going to be simple, because your goal is to approximate the sign from below by some function that will be simple enough so that this integral can be easily evaluated. So, finding this linear estimate is by far the easiest thing that you can do. And now we actually need to compute this integral. But this is now just an elementary function. This is very easy. It's straightforward. So we have 2mr times r, and here we have this constant. So it's actually pi over 2 omega r, and this is computing the integral e to the minus r 2 over pi theta when it goes from 0 to pi half. Now see, this r nicely reduces with this, and 2 reduces nicely with 2, and finally what we get here is that we have pi over omega mr, just as promised, and then the value of this would be when we plug in. Oh, I'm sorry, there's supposed to be minus here, of course. It's a minus, and so when we plug in this minus, so we actually can exploit this minus to first substitute the 0 and then subtract when we substitute pi half. So when we substitute 0 here, it's going to be 1 minus, and then we substitute pi half instead of theta, so it's e to the minus omega r. And this is, of course, for every omega and r. This is a positive number, that is, r is positive here, right? So this is going to be less than 1, and so we can say that this is bounded from above by pi over omega mr, right? And so we've got our inequality here. And so the first part is proved. So actually, if we'll remember where we started, so actually this chain of inequalities leads to the fact that the integral of fz e to the I omega z dz is an absolute value bounded by pi over omega mr. And now for the corollary, it's actually quite straightforward. It's very easy. Now, if we assume that mr tends to 0, right? Suppose that this is defined. This is defined for every r that is greater from some r0. Then, and mr tends to 0 as r tends to infinity. Then this limit of integral over cr of f of z e to the I omega z dz, just by the sandwich rule, since this is non-negative and this goes to 0, then as r goes to infinity, this limit is 0, and we know that complex number or some complex function in absolute value tends to 0 if and only if its absolute value tends to 0. So this limit, as r goes to infinity, of integral over cr f of z e to the I omega z dz is 0. Okay, so the theorem is proved, and now let's take a look at some typical example where this could happen. So a typical example could be if we have two polynomials here, for example, P of z over Q of z, and we try to compute this integral dz over the circular arc. So if P and Q are polynomials, right, and we know by the fundamental theorem of algebra that every polynomial Q of z here has only a finite number of roots, actually equals to the degree of Q, right? So the roots will be spread here in some way, but then since this is a finite set of zeros, then if we take a radius which will be by absolute value bigger than the absolute value of the maximal of the roots, then this expression will be bounded on this circular arc, right? 1 over Q of z will be bounded, and actually if the degree of Q minus the degree of P is at least 2, then the conditions of Jordan's lemma will be satisfied for any two polynomials. So it's a very general case. So now let's see a simple example how we can apply it. So suppose we want to compute the Fourier transform of this function from minus infinity to infinity e to the I omega x dx. This is not such a simple task. If we use real analysis, it's totally doable. But now let's see how we can do it in our case using the residue theorem. So here the function f of z is 1 over 1 plus z squared, right? And let's see where this function is bounded. So if we look at the absolute value of f of z, right, then this is 1 over 1 plus the squared absolute value. And now what I would like to use is this triangle inequality, but the less, say, familiar part. So we know that for any two complex numbers, if we look at the absolute value of z1 plus z2, then everybody knows that we have this type of inequality. And then there is another part that is less, say, famous, that it is bounded from below by this, the absolute value of this. And so we can say that if we plug in here something that is smaller, then it will only increase the function of 1 over. So this would be actually bounded from below by 1 over the absolute value of z squared minus 1 in the absolute value, right? Now, if we plug in z to be r e to the I theta, then what we get here, then the absolute value of this is just r squared, then this is 1 over r squared minus 1 absolute value. So for every r that is strictly bigger than r0, which we choose to be 1, this function will be bounded above, right? And so this is nice. And now we want to apply the residue theorem. So if we will consider this integral, so we now replace this real function by the complex function. So we will now construct this contour. So it's going to be an integral from minus r to r. And here we have this contour. And so we'll look at the integral on this path. So this integral is integral from minus r to r of 1 over, let's say, 1 plus x squared e to the minus I omega x dx, and plus the integral over CR of 1 plus z squared e to the I omega z dz, and it equals the sum of the residues in here. It actually equals to 2 pi I, but now the residues, so the residues are the singularities of can be located only at the singularities of this function. Now this function is analytical, it has no singularities, right? But let's say I plus I omega x, right? And this function here And this function here has zeros at plus I and minus I, but minus I is outside of this contour, right? So we have residues only at I. So it's 2 pi I, the residue of this function, e to the I omega z, divided by y over z squared, the residue at I. Okay, and now, let's see. So as we have seen actually by Jordan's lemma, this integral, it follows immediately. The only thing that you have to show is this, right? That f of z is, it's 1 over r squared minus 1, right? And then you see that it's actually bounded by this constant, right? So f of z for every r greater than 1, f of z is bounded above by this, and it's definitely an integrable function, and therefore by Jordan's lemma, as r tends to infinity, this tends to 0. And then what we have is that the limit of this integral from minus r to r of 1 over x squared and e to the I omega x dx, which is the Fourier transform that we wanted to compute, which is the integral from minus infinity to infinity of this function, e to the I omega x dx. And this is this residue, but so it's 2 pi I. And now, how do we compute the residue of this function? Well, the only singularity is here, and it's a simple pole of order 1. So we take z minus I, right? We multiply it by this function, I omega z, divided by 1 plus z squared, and then we take the limit as z approaches I. And it is just 2 pi I. Okay, and this can be actually decomposed as z minus I times z plus I. So this actually reduces with this, right? And then we have the limit as z approaches I. Here we have e to the, we just can plug it in here, e to the minus omega. And here we're going to have below just 2i. And note how this I nicely reduces, and this is something that we should expect in general, because we have here an even real function, and therefore the integral must be real, and so this I reduces, and this 2 reduces, so we have that this is pi omega, pi e to the minus omega. So hopefully this was somewhat useful to you, and hope to see you in the next video. Thank you.